We're here, again, taking apart complex technical docs and making them, well, actually useful for you day to day. Today, we're hitting a really crucial piece of kit on LNG vessels. We're focusing on the core safety procedures for LNG vaporizers.
That's right. And our source today, it's the instruction manual.
Hmm.
The definitive guide that every single cargo engineer, every cadet really needs to know inside and out. We're looking at the docs for LNG vaporizers and gas heaters. These things are pretty essential. They turn that liquid cargo into usable gas fuel. Big job.
Absolutely. And our goal here for you listening is to really boil down those key safety steps: startup, operation, dealing with problems. We want you to walk away feeling confident, knowing not just what you need to do, but the why behind it, cutting through the noise.
Exactly.
Why do you even need a vaporizer on a ship full of liquid gas? Seems counterintuitive, maybe. We found 4 key jobs it does.
Yeah, 4 main roles. The first one, and this is often the big one in terms of flow rate, is discharging cargo.
Right, when you're pumping ashore.
Exactly. If the shore terminal can't send vapor back to the ship to keep the tank pressure up while you pump out liquid, the ship has to make its own replacement vapor. This vaporizer does that.
And it produces vapor at a specific temperature for this.
It does, typically around minus 140 degrees Celsius. This goes back into the tanks to maintain that positive pressure, usually around 110 kilopascals.
Okay, minus 140°C. Why so specific? Why not just warm gas?
Ah, good question. It needs to be cold enough so that if it hits the cold liquid surface in the tank, it can easily condense. If you pumped in, say, ambient temperature gas, you'd risk creating thermal stresses on the tank. Plus, you could build up pressure way too quickly.
I see. So it's about keeping everything stable, maintaining that cryogenic equilibrium while still doing the job of keeping pressure up.
Precisely. It's a careful balancing act.
Got it. Okay, function number 2.
Number 2 is gassing up. This is done before you load cargo. The tanks will have inert gas, usually nitrogen, in them. You need to displace that heavy inert gas safely.
And you use the vaporizer for this too.
Yep. You supply warm gas, this time controlled very precisely at plus 20 degrees Celsius, to gently push the inert gas out.
Plus 20°C. Quite a difference from minus 140.
Big difference. Shows the control needed. Then third, there's a contingency role, LN2 inerting.
LN2, liquid nitrogen.
Correct. Sometimes, maybe after a dry dock or if the ship's own inert gas system isn't available, you might use liquid nitrogen supplied from the shore terminal. It's extremely cold, minus 196°C.
Wow, colder than LNG.
Much colder. But you still run it through the vaporizer. And again, the outlet temperature is carefully controlled, usually back up to that plus 20°C mark.
Okay, so it handles both LNG and LN2. And the final function.
It's essentially redundancy. It can act as an emergency forcing backup if the main forcing vaporizer has an issue. So yeah, it's a versatile piece of equipment.
Versatile, but that temperature control seems to be the absolute core challenge.
It really is. Which brings us nicely to how it actually works. At heart, it's a steam-heated shell and tube heat exchanger. Simple concept, but the devil's in the details.
Let's unpack that. So, shell and tube. The cryogenic liquid LNG at, say, minus 163°C, or that super cold LN2, is flowing through the tubes.
Correct. Inside the tubes.
And the heat comes from?
Saturated steam. This flows on the outside of the tubes, filling the main body or shell of the exchanger. This steam comes in hot, around 165 degrees Celsius, and under pressure, about 600 kilopascals.
So you have this intense heat source surrounding tubes carrying incredibly cold liquid. How do you stop things from going wrong? Like, how do you prevent liquid just shooting out the end without vaporizing properly or getting the gas way too hot?
Right, that's the critical control problem. You need a stable outlet temperature, and you absolutely cannot have slugging that's pockets of unvaporized liquid escaping. You also don't want superheated gas frying downstream equipment.
So how does it manage that stability? It can't just be the steam flow, can it?
No, it's cleverer than that. It uses what you could call active cooling stabilization. The system actually injects a tiny controlled amount of the cold liquid back into the outlet stream.
Wait, it cools the outlet gas with the inlet liquid?
Essentially, yes. It bypasses a small amount of the incoming cryogenic liquid around the main heat exchange section and injects it directly into the vapor outlet pipe.
How does that work precisely? Just spray it in?
It's quite sophisticated. There's a special spray pipe with usually 2 whirljet nozzles designed to atomize the liquid. But the really smart part is what happens next. There are knitted mesh filters placed right in that outlet stream just after the injection point.
Filters, what do they do?
They do 2 crucial things. First, they break up any remaining liquid droplets into even finer particles, increasing the surface area massively. Second, they create turbulence. The combination turns that injected liquid instantly into what the manual calls a fine fog of liquid gas.
A fine fog, okay.
Yeah, sounds poetic, but it means incredibly rapid and complete vaporization of that coolant spray. This ensures the final outlet temperature is rock steady at the set point, say plus 20 C for gassing up. It prevents overshoot and kills any liquid slugs.
That's ingenious, using turbulence and filtration right at the outlet for precise control. Okay, let's shift gears to safety because this thing sits in the cargo machinery room.
Which is a hazardous area, absolutely.
And it uses steam, which means condensate water that needs to go somewhere, usually back to the engine room, right?
Correct. The steam condenses, passes through a drain cooler, and collects in a condensate drains tank. From there, it's typically pumped back to the engine room feed system.
Now, what happens if something goes badly wrong inside the vaporizer? Like if one of those tubes carrying the LNG cracks or fails?
That is the nightmare scenario. High-pressure cryogenic liquid leaks from the tube side into the shell side, where the scheme is.
So LNG mixes with steam condensate.
Worse, the leaking LNG immediately vaporizes from the heat. Now you have flammable LNG vapor potentially mixing with the steam condensate. And if that contaminated condensate gets pumped
Put it
back,
right into the engine room, a non-hazardous space. That's catastrophic.
utterly catastrophic, introducing flammable gas into the engine room is one of the highest risks on board.
So how do you guard against that? There must be a safeguard.
There is, and it's critical. The system constantly monitors the vent from that condensate drains tank.
The vent line, not the condensate itself.
Right. The tank has a vent line, normally just going to atmosphere outside, but a sample from this vent line is continuously drawn off by the ship's main gas sampling system.
Ah, so it's sniffing the air in the tank's headspace.
Precisely. It's like a permanent watchdog. If even tiny traces of hydrocarbons, meaning LNG vapor, show up in that vent sample, it means there's a leak. A tube has likely failed.
And that triggers an alarm.
A serious alarm. It's your essential early warning, it tells you. Shut down the vaporizer now, isolate it, before that contaminated condensate can get anywhere near the engine room.
Okay, that continuous monitoring is key. Before we talk about actually running it, one more safety point, that liquid nitrogen, the LN2.
Yes. Worth stressing again, people sometimes think nitrogen, it's inert, it's safe. But the temperature,
Minus 196 C.
it's incredibly dangerous. The manuals are very clear. Direct contact causes immediate severe tissue damage. Frostbite doesn't even cover it. And spilling it on deck, just as bad as LNG, it makes steel brittle, causes fractures, structural failure, extreme cold shock. You need maximum caution with LN2.
Absolutely clear. Okay, let's get practical. An engineer needs to start this vaporizer up. What's the very first thing, the golden rule before anything else?
Before any LNG or LN2 even thinks about entering the pipes in the cargo machinery room, two things must be running and verified: the room's exhaust ventilation fans and that gas sampling system we just talked about.
Safety systems first. Always.
Always. If you can't detect or remove a potential leak, you don't introduce the hazard. Simple as that.
Okay, safety systems confirmed. Now, the startup procedure itself. We know it needs to be slow, a phased warm-up. Why is that so vital? Why can't you just, open the main steam valve?
Thermal stress. Plain and simple. You've got this big, heavy steel heat exchanger, probably at ambient temperature, maybe colder. If you suddenly blaft it with 165 degrees steam,
Things expand unevenly.
exactly. You risk warping the shell, damaging the tube sheets where the tubes are fixed, stressing the joints, potentially causing leaks or long-term fatigue failure. That slow, controlled warm-up allows the whole unit to expand gradually and evenly.
Makes sense. So walk us through the key steps for that initial warm-up, distilled from the full procedure.
Okay, first, obviously, check you actually have main steam available and make sure cooling water is flowing to the condensate drain cooler.
Yeah.
That needs to be working. Then you don't open the main steam valve. You find the low-capacity heating steam valve on this unit, and you just crack it open. Gently. A small bleed of steam starts to warm the unit slowly.
Just cracking it open. Okay, what next?
While it's warming, you need to get rid of air and any water sitting in the shell. So you open the shell side vent valve to let the air out. Once steam starts coming out, you close the vent.
And the water.
You also need to open the condensate drain valve to let any trapped water out. You leave this open, letting the unit heat up, watching the condensate drain. The key milestone is when the temperature of the condensate coming out reaches about 100 degrees Celsius.
Why 100 C?
That tells you the shell is basically full of steam. Water has stopped accumulating, and the whole thing has reached a stable, warm baseline temperature. It's soaked through.
Okay, so we're warmed up gently to 100 C. Now what?
Now you can transition to full operation. You close that low-capacity steam valve, VCN630V you started with, then you fully open the main steam supply valve, VCN631V, get the shell up to proper operating pressure.
Steam side ready. Now for the cold stuff.
Only now. You open the main liquid inlet valve and the gas outlet valve. Go to the control room console, set your desired outlet temperature, say, +20 for gassing up. Put the flow and temperature control valves into remote mode so the automation can take over. And then finally, start the liquid supply.
And even with all that automation, the job's not done right. The manual has a reminder.
A crucial one. Once it's running and stable, the operator must do physical checks. Walk around the vaporizer, look at the flange connections, check for any unusual icing, listen for odd noises, feel for vibration. Your eyes and ears are still vital safety tools.
Good point. Automation doesn't replace vigilance. Okay, how about shutting down? Is it just everything in reverse?
Pretty much. But again, it needs to be deliberate and controlled to avoid that reverse thermal shock.
So first step.
Secure the source. Close the main LNG or LN2 supply valve first. Let the liquid already in the unit vaporize off. You watch the inlet and outlet temperatures. They should start to equalize as the flow stops.
Once they're equal.
Then you manually close the vaporizer's own liquid inlet valve, CS601V. After the liquid side is secured, you close the main steam supply.
Steam off. Now, what about the pressure left in the shell? Can't just leave it pressurized or vent it quickly.
No, definitely not vented quickly. You need to depressurize slowly. Crack open the shell side, condensate drain valve again, just a little. Let the pressure bleed off gradually.
Why slowly?
To prevent water hammer slugs of condensed water suddenly flashing or being pushed through the pipes, and also to let the unit cool down gently. Avoid rapid contraction. Once the pressure gauge shows atmospheric, then you can fully open the shell vent valve to be sure.
Okay, startup and shutdown involve careful temperature management. Let's move to when things go wrong during operation. Troubleshooting. This is where an engineer really earns their stripes.
Absolutely. Knowing the alarms and what they mean is critical.
Let's set up a scenario. You're running a stable gassing up operation. Outlet temperature is holding perfectly at +20 degrees C. Suddenly, alarms blaze, the unit trips offline. We want to focus on maybe the most worrying indicator of a serious problem.
For me, that would have to be the low condensate temperature trip,
Yeah.
usually designated TSL temperature sensor, low temperature.
Low temperature
Yeah.
in a condensate. Why is that so bad? I'd think high temperature or high pressure would be the big ones.
High pressure is definitely a concern, yes.
Yeah.
But TSLL, think about it. The condensate, the water coming off the steam side, should be hot, right?
Yeah.
Close to 100 C, maybe a bit higher depending on pressure.
Okay.
If that condensate temperature suddenly plummets, gets really cold, what does that tell you?
It means something extremely cold is getting into the steam condensate side.
Exactly, screams tube failure. The ultra-cold LNG, or LN2, under high pressure, has breached a tube wall and is now directly chilling the shell side. It's one of the most direct signs of a major internal leak. Or, less likely but possible, total failure of steam supply, but usually a leak.
Right. A breach of containment. So what happens automatically the instant that TSLL condition trips?
The system reacts immediately and drastically. A shutdown relay opens, cutting power to the control system's outputs.
Okay, power cut. What does that do?
It instantly de-energizes the solenoids on the LNG inlet control valve and that bypass coolant valve we talk about, SV1 and SV2. They'll fail shut or to their safe position.
So liquid flow stops.
Correct. At the same time, the main pressure and temperature controllers, the PIC and TIC, are forced into manual mode, and their output signal is driven to 0%. And critically, the main automated LNG inlet valve is commanded to slam shut. It physically isolates the liquid supply.
Total shutdown, liquid secured, but the alarm is still active. Can the operator just restart it?
Absolutely not. And this is a key safety interlock. The system stays tripped. Power to those control valve solenoids remains off. To get it back online, the operator must go to the control system interface, the IS Mimic panel, acknowledge the alarm, understand what caused it, and then physically press the reset push button.
So it forces a human intervention, a conscious decision to reset after investigating the cause.
Precisely. You can't just ignore a TSLL and try again. You have to figure out why the condensate got so cold. Was it a real leak? Was the steam supply interrupted? Only after diagnosis and maybe corrective action can you reset and attempt to restart following procedure.
Makes sense. And we should briefly mention there are other important trips too, right?
Oh yes, things like high condensate level LSHH. That suggests the condensate isn't draining away properly. Maybe the pump failed or valve is shut. That can also cause problems, potentially flooding the shell and affecting heat transfer.
So poor drainage.
Right. And of course, there's always the manual emergency shutdown push buttons located nearby.
Okay, so pulling this all together for the listener, what are the absolute key takeaways from our deep dive into this vaporizer?
I'd say three main things stick out. First, respect the warm-up. That slow, low-capacity steam phase isn't optional. It's vital to prevent thermal shock damage. Don't rush it.
Okay, patience during startup. Number two.
Number two, understand and trust the condensate drain tank monitoring. That gas detection on the vent line is your critical early warning for a potentially catastrophic internal leak. Know how it works and what an alarm means.
Got it. Condensate monitoring is the watchdog. And
Third, know your trips, especially that low condensate temperature, TSLL. Recognize it's not just a minor glitch. It's pointing towards a serious potential breach of containment or a major heating failure. Understand the automatic actions it triggers and the need for manual reset.
excellent summary. And of course, the real mastery comes from.
Your specific ship's manual, always. Plus, ongoing training, paying attention during safety drills, that's how you build real competence and confidence with this kind of equipment.
Couldn't agree more. Now, we've talked a lot about the steam side safety and condensate issues. But let's leave our listeners with a bit of a challenge, something to think about based on what we've discussed. We know what a low condensate temperature, TSLL, likely means internal leak, steam failure. But flip it around. What would be your first thought, your first check, if the LNG outlet temperature itself suddenly dropped significantly? Say you're discharging cargo, need maybe, I guess you're 140°C, but it unexpectedly plunges colder. Or if you were gassing up at plus 20°C and it suddenly dove down to -10°C or -20°C, assume your steam supply seems fine. What system would you suspect first?
Yeah, that's a good one. Makes you think about the other side of the control loop.
Exactly. Something for you to mull over and